What is Euler's method, and how can you use it to solve differential equations? Well, let's take a look at this example. dy dx is equal to x plus y with the initial condition y of 0 equals 2. And you're asked, what is the particular solution? Or, can you use the particular solution? And if not, can you approximate the value of y when x is equal to 1? So the first thing you might try when you look at this is the method of separation of variables. But you should see pretty quickly that that's not going to work. Another technique you could try is to draw a slope field for the differential equation dy dx is equal to x plus y. And that would give you a graphical idea of the solution. And if you go ahead and you try and you draw the slope field, you'll see that from the point 0, 2, it looks like this curve will increase and move upward, and so y of 1 is going to be equal to something bigger than 2. But from the slope field, it's kind of difficult to approximate an actual numerical value for the point, for the y value when x is equal to 1. So here's something else that we can try. Let's go to a new slide. dy dx is equal to x plus y, and we know we're starting off at the point where x is 0 and y is 2. dy dx means the slope of the tangent line, so we could use a tangent line approximation. So the slope, which is equal to x plus y, is 0 plus 2 is 2. And the tangent line can be given by the equation, just your equation of a line, y minus y1 is equal to m times x minus x1, or a little simpler to use in this form is y is equal to y1 plus m times x minus x1. That would give us that the y value is equal to the old y value, 2, plus the slope, 2, times the difference in the x values. We started at 0 and now we're at 1, so that's 1 minus 0. So that's our approximation for our y value. That's not bad, but we can do better. Instead of looking at a tangent line going from x equals 0 all the way to x equals 1, let's take smaller steps. So let's make a little bit of a chart to organize our numbers. Starting when x is 0, we know y is 2, and we know the slope there is 2, because remember we're using this dy dx is equal to x plus y. That's giving us our slope at every point. If we take a little baby step and we go to a half, at that point the new y is equal to the old y plus the slope times x minus the old x. Right? The x new minus the x old. Or why don't we just call this delta x, or h? So the y new is equal to the y old plus m times delta x. The new y then would be the new y in this case would be the old y, which is 2, plus the slope times a half, which gives us 3. So let's put a 3 in there. And now we can calculate the new slope. The new slope is 3.5. And now what we've done is, let's just picture what's going on here. We started at the point 0, 2, and we kind of slid along the tangent line to this point where x is equal to a half. And now we want to slide a little further along the next tangent line to the point where x is equal to 1. So our new value for x is 1. Our new y is our old y plus the slope, the 3.5, times the step size, or the delta x, 0.5. And that's equal to 3 plus 3.5 times a half. I'll give you a minute to figure it out. Did you get what I got? 4.75? 4.75. And that's our approximation using a step size of a half. Of course, we could do even better. We can take a step size of a quarter. And by the way, sometimes people use h for this step size. Some people use a quarter. You should be comfortable either way. X, y, y prime. So we need a slightly bigger chart because our step size is a quarter. We're starting at a half. We're starting at 0. We go to 0.25, we go to 0.5, 0.75, and finally to 1. And our first y value is the initial condition that's given to us, 2, and our first slope is 2. Our next y value, is always the y new is always the old y value plus the slope times the step size. So for 0.25, when x is 0.25, the new y value is 2 plus 2 times the step size, which is now a quarter, 0.25. And we get 2.5. And our new slope is now 2.75. And we can continue. You can pause the video for a second and you can try and fill in the rest of the table by yourself, and then come back and we'll compare answers. Okay, welcome back. So I did the rest of this table on my own, and what I got for the y value when x is equal to 1 is 5.324, rounded to 3 decimal places. Did you get the same thing? Excellent. Let's practice our example. So here's a new differential equation. dy dx is equal to 4x plus y. And a curve passes through the point 1, 0. And I'm asking you to approximate y of 2 using Euler's method with 2 equal steps. You could obviously automate this method using a program on your calculator or computer, and you can have a finer and finer mesh, smaller and smaller steps, and you could find a better and better approximation. But on something like an AP exam, you'll really only be asked to use Euler's method with 2 or 3, maybe 4 steps, because that's all that's really reasonable to do on a test, and it's enough to show that you know what's going on. So let's go ahead with this one. Let's set up our chart. We have our x, our y, and y prime. We're starting at the point 1, 0, and we want to get to x equal to 2 with 2 equal steps. So we go to 1.5 and then 2. And at each step, we're going to find our new y according to the equation of the tangent line, which is the old y plus the slope times delta x. So our first slope is, now our equation is 4x plus y is giving us the slope. So our first slope is 4. And our y new is going to be, let's see if we can fit it all here. It's going to be the old y, which is 0, plus the slope times the step size, which is equal to 2. So that's our new y. Now our new slope is 4x plus y. So I have to do 4 times 1.5 plus 2, and our new slope is 8. Now I just have to find one more new y, and then I'm done with the problem. Y new is equal to y old, 2, plus the slope times the step size. 8 times a half is 4. 4 plus 2 is 6. And there is my approximation. Y of 2 is approximately equal to 6. And that's the answer. And remember what this really means. This means that we started at a point x, y. We started at the point 1, 0. And we went along a slope of 4. So we went to the point right here, 1.5 comma 2. And then in our next step, we went along a slope of 8. We went on a steeper slope right up to this point here, where x is 2 and y is 6. And what you see is graphically an approximation of the solution, but more importantly, this number gives you a numerical approximation for the y value at the new x value. And that's a quick overview of Euler's method. Enjoy!